right. Okay, everybody see the screen? Everybody see the slides?
Yes.
Okay, last time we reached slide number 43, 44, right? This is for voltage regulation. Okay, and we said that, you know, we can use the diodes as voltage regulators. Okay, and the good thing about the voltage regulator circuit is that regardless of the current handling capability of the output and regardless of the variation of the VCC, okay, or noise on the VCC, the output of the regulator circuit will be steady, okay, steady. All right. The third application, or one of the application for the diode, is we use it for rectifier. Okay, we use the diode, okay, and rectifier circuit. Okay, as you already knew, okay, and as I explained before, the diode, as shown here on slide number 45, okay, conducts the current in one direction, which means the forward bias, and blocks the current in the other direction, reverse bias. Okay, so in one direction it conducts the current, and the other one it blocks the current. Okay, and this is one of the rules that I put at the beginning of the slides. Okay, that means the current will always go from the anode to the cathode, never goes from the opposite way, from the cathode to anode. Okay. Okay. Now, we usually what we do we're going to convert the AC to DC. Okay. We're going to convert the AC to DC. Okay. Now, AC to DC conversion, the process of converting AC to DC is known as a rectification. It's known as rectification. And the circuit that is going to be used for this purpose is called a rectifier. Okay, so the circuit called rectifier, and the process called rectification. All right. Okay. Now, before designing before designing a rectifier, okay, two parameters, very important parameters, must be specified. Okay, one is the current handling capability required of the diode. Okay, so that means, what does that mean? It means how much current your diode, okay, is able to handle. Okay, how much? Okay, 1 volt, 2 volt, 1 amp, 2 amps, 3 amps, 10 amps. Okay, that's the current handling capability, okay, of the diode. Okay, another thing, another parameter that should be considered, okay, something called peak inverse voltage, better known as PIV. Very important, very important. Okay, where do you find this PIV? You find it, by the way, the current handling capability, okay, of the diode and the peak inverse voltage PIV. You will find it where? In the data sheet of the diode. So before you designing your diode, you have to, okay, select a diode that has enough current handling capability for your design and enough PIV, okay, enough PIV, okay, so that your circuit will not burn or, you know, it will not stop functioning, okay. Okay, so what is PIV? PIV, okay, is determined by the largest reverse voltage that is expected to appear across the diode, okay? And PIV, which is the peak inverse voltage, okay, for the half rectifier is equal to the inverse peak of the Vs, which is the voltage coming from the that is across the diode. Okay, what does that mean? It means, you know, for okay, if you have Vs is like this, what is it? Hang on, what is my pins? Okay, here you go. Okay, if you have the input for okay, if I have the Vs, this is your Vs, for example. If I have it like this, going up, down sine wave. Okay, the PIV for the that you have to worry about is this. This is the peak inverse voltage here. Okay, so this voltage here, which is negative usually. Okay, this is negative. Okay, so this peak is what you have. This is what you have to worry about. Okay, and we're going to talk about it, you know, in more detail, you know, in the preceding slides. Okay, so for now, okay, just know that this is the PIV, which is the peak inverse voltage. That's what they mean by this. Okay, and this is one of the parameters that you have to worry about when you're designing your rectifier circuit. Okay, all right, okay. The rectifier, what do we use it for? What do we use the rectifier for? Anybody? Okay, everybody has a cell phone, right?
To convert A to DC.
Okay, everybody has a cell phone? Yes, okay. Now what happens if your cell phone goes down? You have to charge it, right? So the rectifier is in the charger of your phone. Anytime you want to convert from AC to DC, okay, you need a charger, and the rectifier will be inside it. Okay, guys? All right. All right. And before you proceed in designing the your rectifier, okay, you have to consider a parameter, a main parameter, and that's transformer. You have to know about transformer. Why? Because the transformer will. Why? Because you're going to deal with AC, which is in our country here is what? It's 240 volt. Okay, too big. Okay, for the to rectify. I mean, too big for the charger, you know, to handle in the charger. So you have to reduce the voltage from 240 to say, you know, 10 volt peak to peak, or say 20 volt peak to peak. Okay, so you can deal with it. Okay, 240 is too big. All right. So that's to do with the transformer. Okay, that's to do with the transformer. Transformer will make the big voltage. You can reduce it, or you can. There are transformer that will make the output bigger. Okay, so we call this transformer, and you can see on the right upper corner, these are the transformer that you can find in the lab. Okay, everybody see that. Okay. And the transformer on the left, the upper left, these are transformer. These are in where on villages, old villages. You know, you can see them. Okay, hanging on the pole, electric pole. And down below it, okay, this is a big transformer here. This is, you'll see it in subdivision, modern subdivision, okay, transformer. And to the lower right-hand side of 47, you can see this is not only transformer, but the whole power supply, okay? Power plants. Okay, this is in your high-rise building, say, 20 or 40-story building. The government required you to put a standby power supply, okay? All right, in case something happened, this will automatically come on and power all the apartment in the high-rise building. Okay. All right, now we're going to go deeper a little bit in the transformer, and we see how it works. Okay. Okay, here you go, in slide number 48. This is the transformer on the top right-hand corner. Okay, you can see that the transformer is basically a device that has iron core. This is the iron core, or the core made of iron, and iron is a good provide a good path for the flux, okay, for the flux to travel, okay. And if you have this, you can see on the left-hand side, okay, this is a piece of wire, insulated wire, must be insulated, okay. And you can do it like this. You can wind it around it, okay. And we call this, okay, primary winding, okay, when you wind it like that, primary winding, okay. And when you are winding something like this, the wire around this core, you have to know the number of turns. The number of turns are very important, okay. In this case, we have what? 1, 2, 3, 4, 5, 6, 7 turns, okay. So we call this primary winding, okay. And the voltage that you're going to supply the transformer with is called VP, or primary voltage, okay, primary voltage, or VP. And the number of terms on the primary, we call it NP, okay, this is the number of terms on the primary, okay. On the opposite side, we do the same thing. We have an insulated wire, and the wire is wound across the core, iron core. And of course, we know the number of terms. We call the number of terms NS, okay? This is the secondary winding. And the output of it, call it VS. This is the secondary voltage, okay? Now, when the voltage here is sine wave, okay, it will produce flux, and the flux will come here, travels here to the secondary, and will cut the wires here. It will, of course, it will cut it, and then it will produce this voltage called Vs. Okay, all right. So it has to be AC. Okay, so the transformer will have this side is AC, and the other side also AC. Okay, now watch, when the primary windings, okay, when the number of windings is less than the number of winding in the secondary, okay, is less than the secondary winding, then the voltage on the primary, okay, the voltage on the primary will be less than the voltage produced at the secondary. And when we have that situation, the transformer is set to be step-up transformer. That means you put a sine wave here, for example, 10 peak to peak over here in the primary, the VS will be probably 50 peak to peak, okay, or say, or 30 peak to peak, depends on how many winding, okay, you have on the secondary, okay. So when the winding is less than the secondary winding, that means VP will be less than VS. Therefore, you have step-up transformer. Step-up transformer. And what do we use step-up transformer? We use it at over here. See on slide number 47. Okay, on here on the subdivision. Okay, and on overhead, okay, on villages. Okay, all right. That's we call this transformer step-up transformer. Okay, all right. Now below it we have the same thing. Okay, except here the number of winding in the primary is more than the number of the winding in the secondary. Okay, when we have this situation, that means VP is greater than VS. Okay, which means that the transformer now step down transformer. What does that mean? It means that if we have here a sine wave that has peak to peak, say 115 volt or 240 volt in the primary, the secondary will have, say, 10 peak to peak or 20 peak to peak, much less than here. Okay, on this situation we call it step down transformer. Okay, and this is exactly what we use for our rectifier. Okay, rectifier. So we take 240, we step it down to about, say, 20 or 20 peak to peak voltage here, and then we're going to apply our rectifier circuit, okay, to it. All right. Okay, now on slide number 49, I got this from the internet. This is transformer. As you can see here, the primary winding is greater than the secondary winding, and therefore VP is greater than VS. Okay, therefore, it is, we call this step down transformer. Step down transformer. Okay. Remember that if you want to find what is VS, NP, NS, okay, but you didn't, and VP, okay, of course, this is from the main power supply, okay. Then you can calculate VS. How? Is by using this formula here. Very important, guys, this one here. NP divided by NS is equal to VP divided by VS. And you can solve for VS to find what voltage here you're going to get. Okay. Okay, now, is this voltage here at the output, which is the VS, is it DC? No, this is not DC, this is AC, but it's much less than VP. Okay, much less than VP. Okay, any questions? All right. All right, now rectifiers. Okay, rectifiers are categorized in two. Okay, one core. Okay, the one that we're going to deal with is half wave rectifier. The other one is called full wave rectifier. Okay, now half wave rectifier, we don't really use it in rectification or in any circuit. Okay, why do we use it? Well, this is for illustration. This is for you guys, so that you know what's going on. Okay, after we deal with the half wave rectifier, then we're going to migrate to full wave rectifier, and this is what we use in your charger, okay, for your cell phone, or for your your computers, okay, laptop computers. Okay. All right, now we're going to deal first. This is a half-wave rectifier, which is the easy one to deal with, and that's on slide number 51. Okay, as you can see here, okay, this is, we call this half-wave rectifier, and it contains what? It contains a diode, just one diode, and then RL, and we take the output here, okay, across the RL. Okay, so how does it work? Well, the input here, we're supposed to connect it to VS of the, for the what? For the VS of the transformer. Remember the VS? This is VS here, okay? Which is where? This one here, VS. Okay, so this one here going to diode, okay? But you know, we don't want to draw it all the time. We just, you know, put a voltage supply here, and this is AC, as you can see, and this has a sine wave. Okay, say this one here has a sine wave of 10 volt peak, which means 10 volt, 20 volt peak to peak. Okay, now how does it work? Okay, first of all, you know, to make things easier for us to understand, let's assume that this diode is ideal diode. Everybody get that? Ideal diode means the diode, whatever you put at the input, okay, will appear at the output, okay, which means that the diode will be either open circuit or short circuit. Everybody get that? All right. Okay, now we apply the sine wave here to the input here. Okay, when the input here, when the sine wave is 0, and you have a 0 here coming from the ground here, the diode will be off, open circuit, right? Off. Okay, so the output here will be 0 as well. Okay. Now, when the voltage here, okay, will be say 0.1 volt. Okay, 0.1, sorry, 0.1 volt means, okay, that the diode here, because it's the ideal diode, right? It will be on short circuit. So the 0.1 will appear here. When the input voltage will be say 0.5, this one here will be on. Therefore, the output will be 0.5 as well. So that means the whole waveform, the whole positive waveform or half cycle, the whole positive half cycle will appear at the output, as you can see from here. Okay. Now, once we reach 0, the diode will be off, means open circuit. Okay. When the half cycle, during the negative half cycle, okay, as you
دكتور ما نسمع صوتك.
okay, is it okay now? Is it okay?
Yes, okay.
Okay. All right. So during the positive half cycle, okay, the diode will be on, and therefore the output will see the positive output. The output will be positive. We'll see the whole cycle will pass to the output. During the negative half cycle, the diode will be off, means open circuit, and therefore the output will not see it. It will be 0. Okay, and when you repeat it, you will get this at the bottom here. On, and then off, on, off, on, off. Okay, so this one here is, we call that halfway rectifier. Why? It's because we only have to rectify 50% of the cycle. The other one is wasted. Okay, the other one is wasted. Is there any questions? That, hey, remember this is half-wave rectifier, okay, guys? Half-wave rectifier. Any questions? All right. Let's do it. This is a video here. Does it work? Why doesn't it work? Should work. Something is. I think this slow or stuck. It doesn't even respond. Yeah. All right. Okay, there you go. Okay, there you go. Okay, this is just a small clip of video. Okay. Okay, we start again. Okay, see the positive? Okay, see here? The diode is ideal diode. So the whole positive half cycle is appear here. During the negative half cycle, this is off. So you will not see it at the output. Okay, and then you will see this. Okay, so this is called half-wave rectifier. Notice that we are missing here, okay, the negative half cycle. Okay, so this is just a little video clip. Okay, any questions? All right, very good. Okay, now let's look at the half-wave rectifier output. This is the output of half-wave rectifier, as you can see. Okay, now we want to calculate the average value, or sometimes we call it VDC. Okay, average value. Okay, the average value of a half-wave rectifier is the value that you would measure on a voltmeter. So if you have a voltmeter and you put it at the output of the half-wave rectifier, this is what you get. You get VDC, okay? And you know the VDC, which is this line here, it will calculate the area under the curve. This is the area under the curve. So the area under the curve here is only this positive here. So we take the average value for one full cycle from here to here, or from here to here. Okay. All right. All right. So V average here. Okay, since this is from here to here is 2 pi, the halfway rectifier is only going to use 1 pi. Therefore, V average is equal to Vp or V max divided by pi, or approximately equal to 0.318 Vp or V max. Okay, so this is called V average or VDC. Everybody get that? Any questions? All right. Okay, now over here we said, this is another thing that maybe you should know. Okay, and this is called, the RMS. Okay, so if you have a sine wave and you want to find the VRMS, okay, as I said here, the VRMS value is the effective value of a varying voltage or current. Okay, it is the equivalent steady DC value of which gives the same effect. For example, if you have a lamp connected to, say, 6 volt RMS AC power supply, that will shine. Okay, that will shine. It will give you the same brightness. Okay, when you connect it to 6 volt DC battery. Okay, And that's called, the VRMS. And if you have a sine wave here, like that, and you want to find the VRMS is equal to Vmax divided by √2, okay? Or, how do I remember it? I said VRMS is equal to 0.707 Vmax. Okay, it's the same thing, okay? VRMX is equal to 0.707 Vmax, okay? If you want to calculate Vmax, you divide VRMS by 0.707, okay? And that will give you Vmax, will give you the same thing here, okay? All right. The average value, as we said before, is equal to, this is just repeated, I'm repeating it again. The average value of, or VDC is equal to V average divided by pi, okay, or 0.318 Vmax or V pi, VP, okay? All right, so remember that this is half wave rectifier we are dealing with now, okay? So that you guys understand it full. All right, this is an example here on half wave rectifier. Said what is the average value of half wave rectifier voltage in this figure here, okay? As you can see, this is 50, okay? And therefore VDC is equal to V average over here, okay? And you just divide the peak value by the pi, and that will give you 15.9 volt, okay? Which is about, 31.8%, which is approximately 1/3 of the peak value. Okay. All right, guys. Any questions? Very easy. Very, very easy. Okay. Peak inverse voltage. This is very important. Okay. The peak inverse voltage PIV equals the peak value of the input voltage. Okay. And the diode must be capable of withstanding this amount of repetitive reverse voltage, okay? For the diode in this figure here, the maximum value of reverse voltage designated by or as PIV occurs at the peak of each negative, okay, alternation of input voltage when the voltage is reverse bias, okay? So that the PIV for this circuit or for this diode is equal to minus VP or V peak. Okay, and you know what? They said, we don't want to put negative, okay, value. We don't want to say PV is equal to minus VP. We just have, we know it is minus. Okay, so we just say PIV is equal to PV, which is the maximum peak value. Okay. Okay. Now, where do you find this PIV? You find it, on the data sheet when you want to go and buy a commercial diode to design your rectifier. Okay. Before you do that, you go and look at the manufacturer specification sheet, better known as a spec sheet or data sheet. And you will find that the manufacturer will put PIV, so for example, equal to say 30 volt, okay, 30 volt, okay, and the current I is equal to say 2 amps or something like that, okay. Okay, make sure that when the manufacturer said PIV equal to 30 volts, your input voltage, which is the VS here, its peak value should not come close to 30 volt. Stay away from the 30 volt, okay? If you touch 30 volt, that means your diode will forgive you once, twice, and then third time will quit working. And then you have to throw it away and buy another one. Everybody get that? Okay, got it? So, the PIV for the manufacturer will give you a certain figure, and then you have to calculate your PIV based on the value of the input voltage. So if your input voltage, the peak value, say 20, say 20 volt, okay, peak, then you look at the PIV of the manufacturer and said, oh well, this is I'm way less than what the manufacturer quote in his data sheet. Okay, therefore I'm safe. Okay, but if the voltage that you're going to deal with, say 40 volt peak, and the manufacturer PIV say 30 volt, okay, peak, then you are exceeding the manufacturer PIV, okay, and that's no. Okay, means don't use it. Go, and if you are going to deal with 40 volt peak, then you're going to go and buy a diode that has PIV equals, say, 50, okay, or 45. Get it? Everybody get that? All right. Okay. Any questions? Any questions? Okay, here you go. This is example 2-2. Said draw the output voltages of each rectifier for the indicated input voltages as shown in figure 2-6. Okay, the IN4001 and the IN4003 are specific rectifier diodes. Okay, over here to the left, okay, this is a half-wave rectifier. Okay, and we are using IN4001, which means this is SI, okay, silicon diode. What does that mean? It means that we are going to drop 0.7 volt across it. Okay, what does that mean? It means that your output will be the peak value minus 0.7 volt. Got it? All right. So if you're going to draw the output voltage here, it will be like this, the one that below to the left or in the middle. It will be like this. Okay. This is what, 4.7 volt, which means 5 minus 0.7 volt. That will give you 4.3 volt. Okay. And to the right here, this is IN4003. This is high voltage diode. And you can see this is what, 200 peak to peak. Okay. All right. Therefore, the output will be what? It will be 100 minus 0.7 will give you 99.3. Okay, and it will be unicore like that. Okay, it means you are missing half of it. Now, what is the PIV for this one here? The PIV for this. The PIV for this one here, for this diode, will be 5. Okay, 5 volt. Okay, guys, 5 volt, because this, over here is half the cycle here. Half of the cycle is 5 volt. Okay, negative 5 volt. Over here, okay, the PIV for this is what? Is 100. Okay, 100 volt. Okay, guys, that's the PIV. So your diodes, these two diodes, okay, is way above PIV 5, okay, and PIV 100. Okay. All right. Any questions? Okay. So this is half-wave rectifier. Okay. Center tab. I'm not going to deal with center tab. Okay, because center tab is hardly anybody is using center tab nowadays because of the design of the transformer here. Okay, the transformer has center tab at the secondary, and this is very, very, very difficult and expensive to manufacture. So people tend to shy away from using center tab. Okay. Okay. As you can see on the when we were using half-wave rectifier, we are missing, okay, the half, okay, half portion of the input waveform. That's it. That means half cycle we are missing it. That means you are operating only 50%. That's not good for us. That's not good. Now, how are we going to utilize the whole cycle? Okay, whole cycle. And that's done by the bridge rectifier. And the bridge rectifier is called full wave rectifier. Okay, full wave rectifier. The advantage of this rectifier is that the PIV, when you go to calculate your PIV, will be equal to Vs minus Vt or minus Vd. Okay, which is the Vs over here minus Vd or Vt. Okay, so this is full wave rectifier, which is called the bridge rectifier, and the bridge rectifier is designed as shown here. Okay, with four diodes. Okay, with 4 diodes. All right, this is the simplest way to do it. Okay, and it is connected, to the secondary winding of the transformer. So this is transformer, and over here to the left is the primary voltage here, and the primary winding of the transformer is connected to the AC. Okay, the AC, and the AC in this country, is what 240. Okay, 240 volt. Okay, which is the sine wave. So it runs at what hertz? It runs at about 60 or I believe 61 hertz. Okay, so the frequency of the main voltage is 60 or 61 hertz. Okay, and the voltage is 240 volt AC volt. Okay, all right. Now the transformer will give you step down. So 240, we're going to step it down to say 10 volt peak, or say 20 volt peak to peak. Okay, Vs. Okay, so how are we going to rectify this this 20 peak to peak? So over here you can see that this one here is 10 volt up, 10 volt down. Okay. All right. So how does it work? During the positive half cycle, which is this one here, the red. Okay. During the red positive half cycle. Okay. It will put positive on the top. This is the node here. It will put positive at the top and negative at the bottom. Everybody see that? During this positive half cycle. Okay, remember this is the, over here, this node is connected to RL, to the ground. And therefore, it will put 0, weak 0, it will put weak 0 over here. Okay. Okay, during the positive half cycle, D1, okay, will be forward bias, means on. Okay, and also D2. Why? Because this is 0 at the input, and this one here is negative, so it will be on. Okay, so D1 and D2 are on, and therefore the current will go like this. Okay, through the resistor, and it will put positive at the top, negative at the bottom, and then it will exit from here, and then back to complete the circuit. Okay, so all the positive half cycle, okay, will appear across the output, across the resistor, which is the output here. Okay, so it will appear here. There you go. Okay, this is the V out. Okay, now during the negative half cycle, during the negative half cycle, as shown below here, okay, it will put positive here at the bottom and negative at the top. When it does that, D1 and D2 will be off, okay, and D3 and D4 will be on, because this is negative, this is 0, so it will be on. This is positive, this is 0, this will be on. So D3 and D4 will be on, D1 and D2 will be off. And therefore, as far as the resistor is concerned, which is the RL, okay, the current will flow like this, go like this. Okay, and it will put positive here, negative here, and then it will go to the ground and it will complete the cycle. And therefore, you will get another, okay, another half cycle at the output. Okay, so both the red half cycle and the blue half cycle will appear at the output. Okay, so imagine, you know, that this one here will be repeated at the input, of course, and then you will get all like that: red cycle, half cycle, blue cycle, the cycle, half cycle. Okay. Any questions so far? Any questions, guys? Okay. Let's do the animation. You can see this is half cycle. These two are on. See the output? These two are on. The output will be positive. These two will be on. The output will be positive. And the cycle will continue like that. Okay, guys? Any questions? Questions? Okay. All right. If we want to calculate the VDC or V average, and V average in this case is drawn like this, right? Okay, this is for full cycle. Okay, full cycle. This is the input and this is the output. Okay, so the input is sine wave, the output will be unicore, we call it. Okay, because it's not really sine wave, it's just like hums. Okay, like that. The V average or VDC, as you can see here, is equal to 2 Vm, which is the peak value, divided by pi, or equal to 0.636 Vmax, which is equal to twice the value that you will obtain, okay, for the half wave rectifier, twice. Okay, remember that V average for the half rectifier is what, 0.318. So if you multiply it by 2, you will get 0.636. Okay. Okay, guys. Any questions? All right. Okay. Let's do this example here. Okay, let's do this example. Sit here, determine the peak output voltage, okay, for the bridge rectifier in this figure here, assuming practical model. What does that mean? It means these diodes are Si, okay, silicon diodes, okay, guys, silicon diodes, okay. The transformer is specified to have 12 volt RMS secondary, okay, voltage for the standard 110 volt across the primary, okay. So you know the transformer, he doesn't want you to bother with the 10 ratios for the transformer, and okay, but he said, you know, that don't worry about it. He said, all I will give you that the input at the primary is 110 volt, but the output I will give you at RMS value, which is equal to 12 volt. 12 volt. Okay, so 12 volt means This is RMS. We are not dealing with, we don't want to deal with RMS. We want to deal with peak to peak value at the VS. Okay, so what is it? How are we going to convert the RMS into the peak value? We want Vmax, VS max. Okay, to do that, we know that VRMS is equal to 0.707 Vmax. Therefore, if I want to calculate Vmax, I will multiply the VRMS by √2 or divide by 0.707, okay? And that will give you what? Vmax. So Vmax is equal to 1.414 VRMS. Okay, substitute, okay, and you will see that S peak, okay, is equal to 17 volt. Okay, 17 volt. All right. Okay, so if you have 17 volt, you have two diodes conducting at the same time. So when this one here is plus 17 and over here is negative 17, these two diodes will conduct. Everybody see that? Okay, just like what we just watch in the animation. Okay. Okay, so the value of the V out over here, the V output, will be equal to what? 17 volt minus 2 diode drop, which is in this case 0.7 plus 0.7 will give you 1.4, and that will give you 15.6, as you can see here. So the output will be 15.6 volt. Okay, and if you want to draw the V out, will be like this. Will have 2 amps like that. Okay, and this voltage here will be 15.6 volt. Okay, 15.6 volt. Everybody see that? Okay. If I want to calculate the PIV, okay, for each diode, I will say PIV is equal to V secondary, which is in this case 17, minus 0.7 volt, and that will give me 16.3 volt. Or you can do like what the book is doing. He takes the output and add to 8.7 volt, and that will give you the same answer. Okay. Any questions? Any questions? Okay, guys, here's a question for you. Okay. What's happened if I want to calculate the average value, V average or VDC? What is it equal to? Okay, anybody?
Vmax over 5.
That's for half rectifier. Multiply it by 2 for full
2
rectifier, right? 2 Vmax divided by pi. Okay, all right. Okay, guys. Any questions? Any questions? Okay, very good. Very good. Remember that, this is how you calculate the VDC, which is over here. Let's change color. Okay. I don't know why it doesn't do it. Okay, let's change color. Okay, so this one here, okay, over here. Okay, this one here. We call this one here V average or VDC or V average. Okay, and it is equal to 2 V max, V output max, V out divided by pi. Okay, or equal to what? Equal to what? 0.636 V out. Okay, V out max. Okay, guys. Any questions? All right. Okay. All right. Now back to half-wave rectifier. Okay. This is half-wave rectifier. We're going to improve the output. Okay. First of all, we're going to improve the output for the half-wave rectifier, and then we're going to improve the output for the full-wave rectifier. Okay. As you can see from slide number 63, we have this. Okay, hums. Okay. We don't want to do that. We want the output to be straight. Okay, straight. Okay, or we want to make the hums less. Okay, less. I mean, it varies a lot. We want it to be a little bit. Okay. All right. So how are we going to do that? Okay, that is done by placing a capacitor across the output. Okay, across the output load, for example, in here. Okay, so we place a capacitor across the output, and we call this capacitor, what do you call it? We call it filter capacitor. Okay, filter the capacitor. Okay, okay, right? Okay, guys. All right. Now, as I said here, the output voltage produced by the rectifier circuit is unsuitable for a DC supply for electronic circuit, of course, right? Because it has so many variation. Okay, a simple way to reduce the variation of the output voltage is to place a capacitor across the load resistor called filter capacitor. Okay, the circuit provides a DC voltage output equal to the peak of the input sine wave. Okay, now, when you do that, when we place a capacitor across the output load, as shown here, this is half-wave rectifier, by the way. Okay, now suppose, okay, just suppose. Okay, let's deal with, it's okay, SI. It doesn't matter if it's SI or, let's deal with SI. Remember that SI, it will drop what? 0.7 volt. Okay, during the positive half cycle, the diode will conduct. Everybody see that? Okay, the diode will conduct. Okay, and then what will happen? The capacitor will charge. Okay, will charge. The capacitor will charge to what? To Vn max. This is say Vn will charge to Vn max minus, of course, minus 0.7 because I'm dealing with the silicon diode here. So minus 0.7. So it will be like this. Okay. So if the Vn is equal to 5 volt, okay, this capacitor will charge to what? 4.3 volt. Okay, everybody's listening. I want everybody to be awake. Okay, guys, very important. So it will charge to, for example, 4.3 volt. Okay, if this one here is 10 volt, the Vn is 10 volt. This one charged to 9.3 volt. Okay, guys, 9.3 volt. Okay, during this rise time, during the rise time here. Okay, then it will reach the peak. The input will reach the peak. The capacitor will be fully charged. Okay, fully charged. Okay, now the input will come down. Okay, the output here, will not see this. This edge here. Will not see it. Okay, the output will see the capacitor is already charged to say what to the max, and therefore the capacitor will discharge. Okay, discharge its voltage to the RL, to discharge. Okay, why? It's because once it reaches the max over here, say 4.3, and the input is when the input reach 5 volt. Okay, then below that, if the Vn goes say 4.2, okay, 4.2. If it goes 4.2 and this node is held at 4.3, then this diode will be reverse bias because the cathode is less than the anode. As long as the cathode is greater than the anode, okay, this diode will be off. So from here till to the end, see this one here, the diode is off. The diode is off, completely open circuit, and therefore the output will see only the voltage across the capacitor, and the capacitor will discharge slowly, and therefore the output will be like this. See this? It's going like this, slow. Everybody see that? Okay, so that's the output. Why is that? Because the diode is open circuit. Okay. All right. So it will reach over here. By the time it reach the Vn goes to the max, okay, then the diode will conduct, and then this one here will go like this up. Okay, hang on. Let me produce this. Okay. So when the input goes to the max, okay, just before the max, the output will be like that. The capacitor will charge, and then as the input going down, the capacitor will discharge slowly. So output will be like this. It will have a ripple. They call this a ripple. Okay, it will not be as bad as before. Okay, without a capacitor, it will be much better. Okay, almost straight, except it has a ripple. They call this ripple. Okay, so when we look at over here, got it? So this is the input here. Okay, this is the capacitor, and you can see that the capacitor reach max, and then it will discharge slowly, and then it will reach max, and then discharge through, reach max, discharge, and we call this ripple. We give it, the variable here called VR. Okay, ripple. What is it? Ripple. Everybody got that? Okay. The maximum value that the capacitor will charge to what? 4.3, since the Vn is 5 volt. Okay, since Vn is 5 volt, 5 volt minus 0.7 could be 4.3. This is the maximum voltage that the capacitor will charge to. Okay, got it? All right. So this one is ripple. All right. Okay. As you can see here, this is half wave. Okay, it's supposed to be like this. But because we put the capacitor, okay, it goes like that. Okay, so the output will be not as bad like that. No, it will be green like that. And we call this ripple. This is for half wave. Okay, now imagine if we do the same thing for the full wave rectifier. We do the same thing for the full wave rectifier, then the capacitor will charge, okay, and then it will not discharge completely. It will be halfway discharge, and then the input will come the half, because we reach the peak value of the negative half cycle, and then the capacitor will charge again, and then discharge, charge. So the ripple will be less than the ripple for the half wave. Okay, can you see it? All right. Okay. The ripple here has a, they produce ripple factor. We call this ripple factor. If we want to calculate the ripple factor is called R, the variable R, ripple factor, and that giving you by V ripple peak to peak, which is this one here, from here to here, divided by VDC, okay, divided by VDC, or what do you call it, the average, okay, of the filter output capacity, okay, of the filter output voltage. Okay, guys. All right. Now we come here. This is the half wave rectifier. Okay, and we have this is the capacitor across the output load, and as you can see, we produce ripple. Remember that the ripple here depends on what? Depends on the value of C, to the capacitor, and the value of R. If you put, say, a small capacitor and a small resistor, okay, then the capacitor will charge, but will discharge quickly, okay, through the small resistor. Okay, this is known. Remember what you took in Eeng261, known as time constant, CR. Okay, time constant, CR. Okay. Okay, so when the capacitor is large enough and the resistor is large, then the capacitor will discharge slowly, as you can see here, slowly. Okay, all right. As you can see from here below, the ID through the current here, ID through the current is given by this pulse here. Okay, the pulse, because the diode will conduct only briefly during this time here. Okay, during this time the diode will be on, but the rest will be off, because the work is done by the capacitor actually. Okay, all right, and the IL here will be what? Will be what? V out divided by R, and it will give you the same result as this one here. This is V out. Okay. Now for the half rectifier, the ripple VR is equal to VP, okay, output divided by FCR, where F is the frequency of the input. Okay, frequency of the input. If the frequency is 60 Hertz, then F would be 60. And CR is the value of the capacitor, and R is the value of the resistance. Okay. And the current I average will give you, given by IL is equal to 1 plus pi root 2 V out divided by VR. And for ID max, it will give you the same, except that you have to multiply it by 2. Okay. All right. Remember, hey, you guys, remember that's F. Don't forget F is equal to 1 over T. Okay, where T is the time constant over here. This is the T. This is the time for the full wave. Okay, this is the time for the full wave. All right. Or we call this what we call it? We call it the period. F is equal to 1 over T, period. Okay. Any questions? All right. This is blank here. All right. Okay, as you have seen before, okay, I is equal to V out over R, we saw that, and then ID is equal to IC, which is the current through the capacitor plus the current through the resistor. The current through the capacitor is given by C dV over dt, and then plus the IL. Okay. Over here, you can see this is the ripple. Okay, we call this ripple. Okay, VR. As you can see, this is peak-to-peak ripple. Now, notice that VDC is not like before, which is V for the half rectifier is V out max divided by pi. No, VDC or V average will be much, much better. Will be over here. This is VDC. Okay, this is VDC. And VDC is given by this formula here. VDC is equal to VP, which is the V max, okay, output, minus VR divided by 2, okay, or equal to V average as well. Okay, so this is VDC. Okay, and this is for full wave rectifier. For full wave rectifier here, V ripple is equal to VP divided by 2 FCR. Why 2? Is because you are dealing with double the amount of voltage of the half wave rectifier. Okay, and that's why you multiply this by 2. Okay, and therefore VDC will be this one here. Okay, and the currents will be the same as before. Okay, all right. Any questions? Okay. So we reach slide number 70. We stop here. We're going to stop here, and then if there is any question, let me know. Is there any question, guys? Any questions?
دكتور اللاب كل ثلاثة ويا بعض ولا كل واحد؟
No. This is a lab for individual. I said that already. Okay. Keep. All right. You don't have to save. Don't save. Is there any questions again? Okay, we stop recording.